questions about integration. There's this interesting thing, it would be nice to just sort of drop it into like the Halo 2 toolchain. But Halo 2 uses univariate polynomial commitment schemes, and Lasso uses multilinear ones. And so that sort of mismatch is complicated. But I think there might actually be some polynomial commitments that actually just already exist and bridge the gap. I have to look more closely, but this paper called Gemini gave sort of a generic transformation from univariate polynomial commitments to multilinear, and that might sort of just let people use the same, KZG powers a tau setup and commitment scheme, directly within Lasso. So I got to chase that down. That should literally just be like, remind myself in full how the Gemini transformation works. If that works out, then I think you can literally just sort of slot in Lasso as a lookup argument with that, anywhere people are explicitly using lookup arguments today. But if that does not sort of directly work, then it will be much harder to integrate Lasso into all of the existing univariate tooling. And so that it might just be that sort of either everyone has to switch over to using multilinear polynomials, or else they kind of can't really use Lasso easily, if that makes sense. Is that a little bit helpful?
Yeah, I think so. I mean, by open source, you mean you release the papers?
So the papers are out and the code is out. But the code is just...
Where's the code? I haven't found it for some reason.
Oh, interesting. I think
Oh, there. I see a link, maybe open source implementation here, kind of hidden in this blog post. Let's see. I think I just found it. Yeah, there it is. Okay, great. Nice.
Yeah. The implementation right now is just Lasso. And so the entire Jolt paper is everything in there is sort of not implemented. Jolt uses Lasso as like a subroutine sort of. And so everything that's in Jolt that is not literally, Lasso, still needs to be built. It would be nice if anywhere people use lookup arguments today, you could just directly plug in Lasso, and sort of, but there is this gap just between univariate and multilinear polynomials, and almost everything people are using today is univariate. So that, I think that's the main bottleneck to that vision. There is also, sort of the conceptual point that the way people use lookup arguments today has maybe been limited by the capabilities of existing lookup arguments. So now that Lasso is around, it's possible people will just start using lookup arguments in ways they haven't thought of before. In which case, the goal of just sort of swapping out any application of an existing lookup argument, just putting Lasso in for the lookup argument might itself be pretty narrow a goal. Maybe the right goal is to re-envision how we use lookup arguments and what we use them for, rather than just go around and swapping out lookup argument everywhere.
Yeah, that's pretty interesting. I do have maybe more questions or comments, but I don't know if you want to start, or I don't want to take up too much time.
Yeah, I mean, I think, normally I find the most interesting discussions in this meeting just come from questions, and rarely, does a question take a long time and not, add anything. So I'd say just go ahead and ask.
Sure. Okay. Yeah. So I've been sort of digging around into ZKVM design, which is why this is really interesting, because it seems like it's kind of, as you say, a new paradigm.
Mm-hmm.
The project I'm working on right now is emulating like the MOS 6502. And I'm doing that though in Noir, which is like quite slow. But eventually, obviously, Noir has this intermediary representation. They have kind of swappable backends. So I think they would be able to use, like, as you say, plug in Lasso, especially once they shift over to Honk in theory, right? Because that is multilinear. That's the sum check protocol at the heart of Honk. But there's also this other meta point you're bringing up, which is like maybe, there should be like a new kind of tooling or a completely new approach. Is that correct interpretation?
Yeah. I think that's exactly sort of how I think about it. And I don't know, outside of, well, I can say more about, I'll elaborate on, the different ways I see of using lookup arguments, sort of moving forward. I have some thoughts on that. But I think sort of Aztec is better positioned to just slot in Lasso, because they're already moving to some check-based and multilinear polynomial-based things anyway. And I actually suspect that, this zero-morph polynomial commitment sort of is, it basically is like what I said, Gemini applied to KZG to make it multilinear, with zero knowledge added on and some optimizations. And my guess is, like, in the short term anyway, that will probably be like the most popular polynomial commitment scheme to use, because it sort of has the shortest proofs amongst the multilinear ones. And if you care about ZK, it's ZK and stuff. So yeah, I am hopeful that that's sort of the direction. Yes, it's sort of fortuitous, I guess. But if the Noir folks, think that Lasso is like a good lookup argument to use, that they should be well positioned to do it. So to elaborate a little bit more on kind of different uses of lookup arguments opened up by Lasso. It was a little hard to describe. The A16Z, like, communications people who were helping, with the blog posts, really, wanted to say things like, there was just no way to handle like gigantic tables before. And it's sort of not. It's both true and not true. As with many things in this space, things are just nuanced. Because the way Lasso works is by taking a giant table and decomposing it into small tables. You actually could have taken this sort of approach. In fact, people basically are already. It's just that the decomposition of the big table into the small tables is sort of two things. One is Lasso sort of wraps that, like encapsulate that decomposition and putting together, the small table lookups into the big table lookup, encapsulates all of that inside the lookup argument, so the developer doesn't have to, think hard about that, themselves. And then the other issue is just the sort of the decomposition and recomposition is done like at much lower cost in Lasso. Basically, I guess you could think of it as everything is sort of handled by some check, and there's no commitment costs to do the decomposition and recomposition. Whereas, like most of the univariate techniques would involve extra commitments to like intermediate values as you're doing the decompositions and recompositions. So in a sense, you already could have done a lot of what we're trying to do here. It just would have been much more expensive. And the perspective of like, doing one lookup into a big table, I think is useful, just sort of leads to, this sort of lookup singularity notion that otherwise, might not have been obvious. But so let me just mention like a new application or a new way of using Lasso, which I'm going to put into an upcoming blog post, but sort of isn't actually public now, which is the following. So there are some functionalities that are probably most naturally captured by Boolean circuits. Things like, standard hash function evaluation, whether it's SHA-2 or, Ketchak or whatever. And yeah, certainly the way, I don't know, it's fairly natural to like compute one copy of SHA, by just doing everything bitwise and using like AND and OR gates, just because of the way people designed SHA, sort of naturally a bunch of ANDs and ORs and so forth. We thought hard about whether you could sort of use Lasso to speed up a snark for proving knowledge of like one copy, for snarking like one copy of SHA. And you can get some speed up, but it's sort of a little bit underwhelming. So I actually think the right way to do things is as follows. So in most applications, there's some amount of data parallelism, and this actually naturally happens with hash evaluations because, like, most of the time, the hash evaluations are sort of coming up, because they're actually there's some Merkle authentication path that you're proving knowledge of or something like that, and so if there's one Merkle authentication path, maybe you have something like 20 hash values you have to prove knowledge of. But if you're dealing with many Merkle authentication paths, you might have thousands or 100,000s or millions of hash evaluations. And so there, I think the right approach is as follows. And the computer architecture community actually has a term for this. It's called bit splicing. So let's say you want to evaluate SHA on like 64 different inputs. So you would take like the first bit of each of the 64 inputs and pack it into a single field element. And then the second bit of each of the 64 inputs and pack it into another field element and so forth. And now, like if you take a single circuit for SHA, like each AND gate turns into like a bitwise AND on like 64 bits. Just because you're evaluating, that AND gate like independently on 64 different inputs, but like all 64, things have been packed into like one field element. And so you're just directly turning individual ANDs on individual bits into like bitwise ANDs on field elements. And that's like exactly the thing that Lasso is good for. And so I'm like sort of increasingly amazed by like the direct parallels between the way people design like real hardware that runs on, like actual silicon and snark design. I've talked to some people who think like this is not amazing. Like, snarks use circuits and like real hardware uses circuits. And even though they're not really the same kinds of circuits, like we should expect generally like similar design principles to work, but it seems to go like even more. It's just like literal. There's a Wikipedia article like on bit slicing in computer hardware, and that literally seems to be like, and for almost the same reasons, potentially the right way to use Lasso in certain for certain functionalities. That seems like more than there's some kind of deeper explanation there than just, well, snarks like to use circuits and real computers like to use, a different kind of circuit and but they're similar enough. But again, the lookup tables for bitwise ends, in principle, you could use existing lookup arguments already. It's just, I think Lasso does it more efficiently and sort of puts all the details of decomposing the big table into small ones like inside the lookup, so the developer doesn't have to do it themselves. Was that helpful?
Yeah, that's really cool. And kind of also your point about the parallels to hardware sort of leads into the next question. I think, and my last one, because I have to kind of drop out a little bit early, but yeah, I've noticed the same thing 100%. And from some of the conversations I've had, it seems like there is a kind of race to determine a sort of something like a risk architecture, which I was talking to Frank Laubert, like Risk Zero, and he was saying that all modern processors actually use like even x86 uses RISC-V like underneath the hood. It's called micro ISA. And so I think I guess this is just kind of a question about where you see the ZKVM design space going more generally. Is do you think something kind of similar is going to happen where you'll have this sort of like micro ISA for the ZKVM, and then everything else is abstracted from there. You're just sort of, you don't even have to think about the ZK part.
Yeah, great question. Yes, the short answer is yes. So this is another thing that amazed me recently. So I'm not, my background is not in computer architecture. So I was literally asking Chat GPT to explain recent trends in computer architecture to me, in particular RISC versus CISC, complex instruction sets versus reduced. And apparently, the line between CISC and RISC has gotten seriously blurred because the way people actually implement complex instructions is basically just by turning them into reduced instructions. Something along those lines is what ChatGPT told me. And so that's exactly the sort of thing that we're kind of seeing fall out of the lookup singularity approach to ZKVM design. And so, the Lasso approach to ZKVM design sort of says all primitive instructions are of equivalent complexity, equivalent snark friendliness, as long as their evaluation tables are, decomposable or, MLE structured or whatever. And that sort of suggests that you should make the primitive instruction set kind of as complicated, as you would like, up until the point that they no longer become decomposable or MLE structured. If you want to do anything more complicated than that, then perhaps the right approach is just to break your complicated thing into several, simpler things that are decomposable or MLE structured. Now, in real computer hardware, there's really no reason at all for the notion of decomposability. Well, sorry, decomposability actually is just intuitive enough that maybe real hardware is kind of taking advantage of that. I don't know for sure, but you could definitely imagine that the fact that a bitwise end can be computed by breaking things into chunks and doing a bitwise end on each chunk is useful for real hardware. I don't know. So MLE structure, multilinear extension structure, that is not something that I can imagine directly coming up for real hardware, but the decomposability thing I could. So there could be some cosmic coincidence where decomposability is the key to real hardware, and it's also the key to ZKVMs. And so the same things people do in real hardware, or is it what people should also do for ZKVMs? So I guess that's most of my rambling thoughts. I should probably talk more to some people who actually know something about hardware and see if it sounds sensible to them.
Yeah, it's super interesting. I'm also very curious about that, and I think I'm operating sort of one level above, right? At the moment, I have to get into the details, but I think for the whole space to move forward, you kind of have to get to that point of abstraction.
Mm-hmm. Yeah. And I am hoping to put out like that, some extra blog posts and, maybe this ZK study club session in a couple weeks will make it a little easier. So right now there's just like 100 pages of papers. But I sort of, I agree. I think the main thing to grok at the moment, I guess, is the following. Hopefully, this comes out of my mouth reasonably. So if you don't worry about how like Lasso works, if you just want to think about how to use it in like the cleanest way, the way I think about it is. It's sort of a general improvement over like bit decompositions, right? So like the old way of doing things that didn't easily turn into additions and multiplications was to have the prover provide as untrusted advice, like the individual bits of the data type, and then just like compute everything bitwise, because you can always compute anything bit by bit, just because like ends and ors are a universal gate set. And sort of what Lasso lets you do is just pack a bunch of bits into a single field element and, do things that are natural bitwise, but are not natural, as like field additions and multiplications, with costs that are like much closer to like just doing like one addition or multiplication, right? So I guess one lookup with Lasso into like a size, 2 to the 64 table should be some, let me just do the math real fast. So it'd be like 3 times 3, C would be like 3 there. Yeah, okay. So I think the prover basically commits to something like 10 field elements, and they're each small. So that's about the cost that like Planck pays for like one addition or multiplication gate. So, at some very high level, you can do, one operation that's sort of natural to do bitwise, but not with the cost of like a single multiplication gate or addition gate in Planck. I'm trying to just think of Lasso as like a hammer that kind of lets you do something that is natural to do bitwise, with roughly the same cost as existing snarks would do for a single multiplication. So if maybe that perspective is helpful in just sort of understanding what the new techniques can achieve, even though it doesn't sort of tell you at all how they work under the hood.
Yeah, no, great. I think, just as a starting point too, for my intuition, I think that is very helpful. Thank you.
Mm-hmm. Yeah, thanks for the questions.
I have a follow-up, and I'm maybe extracting too much from what you just said, but then is Lasso intended, I guess the like killer use case, so to speak, for Lasso is like VM design, or like what's the thought?
Yeah, that's a great question. This is something exactly what I want to discuss in sort of my next blog post. So I think of VM design as one application of Lasso. It's not the only one. So, the same way that like people use lookup arguments already today, whether they're designing a ZK VM or like, not. So I think it's sort of a technical hammer, which is why it's a little hard to explain. All of you kind of can understand like what a lookup argument is, right? But like, talking to somebody who hasn't thought about snarks before, it's very hard to explain like what is a lookup argument and why is it useful. I think. So right now I have sort of two clean uses of Lasso. So one is into ZK VM design, as in the Jolt paper. The other, I don't know when you joined the call, but I was talking about using it for like evaluating something like Ketchak or SHA-2 or something on many different inputs, and you're sort of wielding it in conceptually different ways for the two applications. So it's like Ketchak is like not something that's very natural to compute. In a virtual machine abstraction, you kind of want to deal with it at a lower level of abstraction. So you kind of want, conceptually, even if, in the end, it's sort of, you're just applying lasso. So of course it's doing the same thing under the hood. You wind up using it in a different way. So yeah, I think the right way to think of lasso again is just like things that are natural and simple to do bitwise, but are not natural and simple to do when all those bits are packed into a single field element, and your primitive operations are addition and multiplication over the field. Lasso kind of just lets you do those things with roughly the same cost as if they were amenable to being done as finite field additions and multiplications. And that's just like a useful thing anywhere.
Yeah. Yeah, that makes total sense. And so are we going to get in today, like how that works?
I can try. Sure.
Well, I was just curious. Yeah.
Yeah, I guess. Yeah. So it'd be sort of helpful for me to try. I don't know how well it would go. And when I talked about sparse polynomial commitment schemes previously, this would be sort of representing some of the same stuff, but I think it's one is I might do a slightly better job. The other is you sort of can't just see the stuff once. Anyway, so I'm happy to dive into that. We can also see if there are more questions first.
Well, I think the agenda was per the flow was for ZK today, so it wasn't like necessarily a request, and I was just curious, like what. Maybe if we were going to touch on it today, or we can go to the paper and kind of compare to the sparse PCS. Offline.
Yeah, sounds good. Yeah, so someone in the chat requested more lasso discussion today, which and then I literally just forgot to show up last night because yesterday was a little overwhelming. So it's probably good to not move to ZK today, and we can do that next time. I might have one final off week next week, but then things the travel for the summer is done at that point. So let's plan to defer the ZK discussion till next meeting. And yeah, we'll just chat about lasso today. Does anyone want to ask anything else? And if not, I can just start. I'll share my screen and see if I can say something useful about the details.
Yeah, I had one more, and you may touch on it as we get into it, but you mentioned earlier, it said something that's MLE compatible. I'm just curious, what your definition of that is.
Yeah, great.
Yeah.
Great. Yeah. So, okay. So we frame lasso as applying to gigantic lookup tables, meaning, size 2 to the 128, or, so big, even if I gave you all the computers in the universe, you couldn't write down the whole table. So, then we say, it comes for free almost to use a giant table. No one actually has to materialize it. The prover only winds up kind of paying in runtime for elements of the table that are actually looked up, right? So if you only look up 1 million elements of your table of size 228, you only pay for those 1 million elements. Now that is impossible if your table is just full of random unstructured junk, right? Because then there's no way to even specify the table without just writing the whole thing down. So the question is what structure does the table need for all of this to work out that no one actually has to materialize the whole table? And lasso the paper has 2 different kinds of structure. So one, broadly speaking, one is more general, but the protocol we give that handles that sort of more general structure is a little bit more expensive than the protocol we give that handles the less general kind of structure. Okay, so the less general structure is what we call decomposability, which basically just says that you can sort of do a lookup into the big table by doing a handful lookups into much, much smaller tables. And I'll give you an example in a second. But then the other structure, which is more general, is this MLE structured thing. Okay, and that is the following. Think of the table as like a giant vector of size of length to the 128. And for any vector, you can define its multilinear extension polynomial. And that will be a polynomial in like 128 variables if your table is size 2 to the 128. And so it's possible to for that multilinear extension polynomial to be evaluatable in time, just like 128 field operations. The vector might have size 2 to the 128, but you might be able to evaluate the multilinear extension at any desired point with only like 128 field operations. Okay, that's what MLE structure means. And so the most general kind of tables we can handle are these MLE structure tables. Actually, it doesn't even need to be the multilinear extension. Any low degree extension would be okay. And like in theory, that's like a very, very general class of tables that actually, in theory captures like kind of any table where like the mapping of indices of the table to the table element that lives in that index. Any table where that mapping can be like computed by an efficient, like a small circuit that operates on the bits of the index, is low degree extension structured, like conceptually. So it's a really, really big class of tables that we can handle in theory. Okay, but like in practice, it seems everything that matters is actually decomposable. The JOLT paper, actually shows that you can build a ZKVM for RISC-V completely out of decomposable tables. So you actually can use like the more efficient variant of Lasso that applies to decomposable tables to build the ZKVM. And so just to wrap this up, I want to give an example of decomposability, like a giant table that's decomposable into small tables. And I think the cleanest example is actually bitwise end. Okay, so let's say you want to, you have two 64-bit data types, and you want to compute their bitwise end, which is 64-bit output. So you can do that by breaking, the 64-bit data types into a bunch of blocks, a bunch of chunks. Say 8 chunks of 8 bits each. Or I guess you should think of them as sort of eight chunks of 16 bits each, because, the two inputs together is actually 128 bits. And anyway, so the bitwise end of the two 64-bit inputs, you can actually compute by taking the bitwise end of each chunk, right? And then just concatenating the outputs. Okay. And, in translating that into like lookup table terminology, that's just saying that, the table size 2 to the 128, that just contains like all possible evaluations of the bitwise end instruction. You can sort of decompose a lookup into that giant table into say 8 lookups into a table of size 2 to the 16. Right. And the decomposition is really just, it's doing what I said, is taking your two 64-bit inputs and breaking them up into 8 chunks of 16 bits each, and, computing the bitwise end of each chunk and then concatenating the results together. And it seems that like everything people like need to do in practice is chunkable. Maybe we should have called it chunkable instead of decomposable. So, hope that was a little bit helpful.
I think I'll have to read the paper to understand like what the efficiency gain is by decomposing.
Yeah, well, okay, so what it boils down to is like all lookup arguments have some cost for the prover that depends on the table size. And so you can't just sort of directly deal with a gigantic table, because there'll just be some cost to the prover that becomes astronomical. Okay, so that's the reason to break lookup into a gigantic table that's way too big for anybody to, pay a cost, proportional to its size, into several lookups into smaller tables. Okay, now in all like prior lookup arguments, so Lasso does completely avoid certain costs that are linear in table size that appeared in prior lookup arguments. So in particular, in every prior lookup argument, an honest party in pre-processing would have to cryptographically commit to the table. Okay, which means there's actually somebody honest has to pay like a cryptographic cost that's linear in the table size. So Lasso completely avoids that for structured tables. So where Lasso like does pay a cost that's linear in table size, if this is where it gets technical, but if you want to know like in the technical weeds, where is that cost like still appearing in Lasso? The answer is actually in the evaluation proof for the polynomial commitment scheme. The polynomial commitment scheme that's used inside the lookup argument. We do not need an honest party to cryptographically commit to the table in preprocessing, but we ultimately do need the prover inside the lookup argument to reveal an evaluation of a polynomial that is as big as the table, and to keep that cost from being astronomically big when we're dealing with these astronomically big tables. It's essential to decompose the astronomically big table into smaller tables that you can afford to pay that cost for. Does that make a little bit of sense?
Yep. Mm-hmm.
Yeah. So, and that's exactly the sort of technical detail that's hard to explain in full, and what I should try really hard to convey, in upcoming either blog posts or presentations or something. For that, you actually have to go into the guts of how lassos work and under the hood.
Well, I think what's interesting, and maybe this would be helpful in structuring whatever you write, is the evaluation, and I'm mixing some topics here, but the commitment at that last in the prover. How do I say this? I think it ties back to actually how the proving algorithm actually works, and this is just a function of that. So like zooming in on that micro step, that micro last step, as like an educational piece might like illuminate why there is some sort of like technical overhead in a linear fashion.
Yeah. I think you're hitting the nail on the head. I can say something now, and actually it might be helpful if you let me know if this is helpful, which is the following. Okay, so if you have a giant table, say size 2 to the 128, but you're only doing like 1 million lookups into the table, okay, you're intrinsically going to get some kind of sparse vector arising, right? Like the vector has size 2 to the 128, but you're only doing 1 million lookups, so only 1 million entries are non-zero. Like that's just somehow that's naturally going to arise in the protocol. Now, so there's a question of how do you cryptographically commit to a giant vector that's very sparse. Now, with MSM-based commitment scheme, you actually can do that very straightforwardly in time proportional to the number of non-zeros, because just the way MSM-based commitment schemes work is you take each non-zero, and the way they work is like the entries of the vector are thought of as exponents, and anything to the zero is just 1, so you can just ignore it. Like the way Peterson vector commitments work is you just it's called an MSM or multi-exponentiation, but like you just take all these exponentiations and you multiply them together, right? So if you multiply a bunch of things together, ones just don't change anything. So what that's saying is like the committer can literally just ignore the zeros. Okay, so committing to a gigantic sparse vector is simple. So why don't people just do that and they're done? Like why is that enough to deal with these giant sparse vectors in these lookup arguments? The answer is because at the end of the lookup argument, there's going to need to be an evaluation proof from like the commit, involving the committed polynomials, which are derived from these giant sparse vectors, and there the sparsity no longer helps. So there you actually would wind up paying cost that's linear in the size of the vector, regardless of how sparse it was. And so the whole name of the game in all of these lookup arguments is exactly to deal with that. So if you look at like the Calc line of work, the way they actually commit to these sparse vectors is exactly what I just said. And then they do very clever things to try to sort of minimize the cost of the opening proof. And the way Lasso works is a little bit different. Like, we sort of never have the prover directly commit to that giant sparse vector at all. The prover instead commits to what I call a much shorter vector, a dense vector, that kind of just lists where the non-zero entries are in the sparse vector. And that's sort of the difference, the qualitative difference, like between like the Calc line of work and Lasso, where it comes from. And we don't say this in the paper, and I haven't said this in any blog post, so I should write a post that explains this. Like Lasso like directly commits to the giant sparse vector, and Lasso, the Calc line of work, and is very clever about how to kind of deal with the linear in cost of the opening proof, whereas Lasso sort of never commits to the giant sparse vector in the first place. Instead, it commits to an equivalent representation, which is just like a list of the non-zero elements of the giant sparse vector. Did that make a little bit of sense? Enough that it's worth trying to say in a blog post or presentation?
The question that I would have after hearing that is, like, do you have to commit to the locations of the sparsity in order to make it like well, I guess maybe not if you can like index. I'm just like literally thinking out loud here, but like what are the vulnerabilities in doing that way, if any? And that would be like the final question.
Yeah, I mean, so there are no vulnerabilities. I mean, sort of the whole point of the Lasso paper is to make sure of that, I guess. So let me think if I can say a little bit more. This is sort of getting into how does Lasso work? So maybe I can say a sentence about how Lasso works, like on in its guts, which is. So this giant sparse vector like naturally arises just because the table is gigantic, but you only sort of look up a handful of entries of the table. The way Lasso commits the giant sparse vector, right, is it literally just lists the non-zero entries of the vector. Okay, and so that is now itself a vector, a much shorter one. It's just a list of the non-zero entries in the giant sparse one. And so in Lasso, the prover just commits to that. Okay. And then in these lookup arguments, so it commits to that vector, which is now, not giant anymore. And then in these lookup arguments, like at the end of the protocol, the verifier has to evaluate sort of the giant, a polynomial derived from the giant sparse thing at a random point. And the Lasso prover, like literally what it does is it proves the following. It says it proves it correctly ran an algorithm that takes as input like the list of non-zero indices of the giant sparse thing and spits out the associated requested evaluation. Okay, so that's like, that's a complete description of how Lasso works. Again, the prover just, sort of commits to the giant sparse thing by instead committing to a list of the non-zeros in the giant sparse thing. And then later proves that, when the verifier says, hey, let me evaluate the giant sparse thing at this point, the prover proves it sort of correctly ran an evaluation procedure whose input is like just the list of the non-zero entries of the giant sparse thing. So the only thing I'm not telling you is just, how does the prover prove it correctly ran that algorithm? Was that helpful?
Yeah.
Okay. Yeah. So I'll that's how I'll go ahead and like try to present things like, this is what Calc does, this is what Lasso does, and then the rub will just be, if I can give additional details about how Lasso actually the Lasso prover proves it ran this algorithm correctly. Cool. Any other questions?
I have questions about the paper. So you can only think of it. I think if I'm not wrong, you can only think of it as a matrix when C equals 2, right? So if C is greater, it's like multi-dimensional.
Oh, interesting. So you're referring to this like sparse matrix M that arises in the paper. So the prover's claiming that.
Yeah, because in the paper the example is like C equals 2, and so you have column and rows.
Yeah. So I would say even when C equals 2, this issue is kind of already present. Okay, so when C equals 2, what we're doing, that matrix M, which it has, if there are little m lookups into a table of size n, that matrix M, capital M, has little m rows, one row per lookup, and n columns, like one column per table entry. Okay, when C equals 2, what we're doing is we're decomposing the n column. So like, I don't know if you want to think of it as the table itself, since there's one column per table entry, into like a square. When C equals 3, we're decomposing it into a cube, and so on and so forth. So it's that the matrix capital M is a different matrix than the matrix I think you were referring to in the C equals 2 case. Does that make sense?
Yes, I think.
Yeah. Okay. So that C parameter, so the prover cost in Lasso, there's basically there's some cost that grows linearly with the number of lookups, and then another cost that's like table size to the 1 over C. So that the C, you were mentioning is exactly that C, table size to the 1 over C. And the way you get table size to the 1 over C is like kind of by viewing the table as a cube. As a square if C equals 2, as like a 3-dimensional cube if C equals 3, and as a higher dimensional cube if C is bigger than 3. And sort of, conceptually, I guess the prover is kind of paying for only like one dimension of the cube, right? So like, a 4-dimensional cube, like, each face of the cube is of size, like, total cube size to the 1/4 and so forth. So the bigger you make the dimensionality of that cube, like the smaller this price the prover pays, that's proportional to one face of the cube. But there's a tension because it makes the more dimensions of the cube there is, the more you pay per lookup. So yeah, in general, the costs are sort of like for the prover are like 3C field elements committed per lookup, plus like end of the 1 over C is like a fixed cost regardless of the number of lookups. So the bigger C is, the smaller the fixed cost, but the more you pay for each individual lookup.
So C is the bigger the better until it's like dominating.
Exactly. So you're sort of, the protocol designers incentivize sort of to set C so that the number of lookups M is about equal to table size to the 1 over C. Exactly. And so that's why, like in Jolt concretely, most of our tables, for 64-bit data types would have size 2 to the 128. And so we wind up suggesting to set C to be like, 6 or so, so that table size to the 1 over C is something like 2 to the 22. And that means that, you're sort of setting the two costs equal, so long as you're running like the RISC-V machine for at least 2 to the 22 steps or something. Because there's one lookup per step of the RISC-V CPU, more or less. So you want to set the two costs equal. That's sort of the optimal value of C, roughly. There's some small intricacies, but that's the top level way to think about it.
And the memory checking thing is to make sure the like what's its purpose, I guess.
Yeah. Okay. So, in some sense, a lookup argument just is doing memory checking. Okay. So the whole point of memory checking, like a lookup table is just it's a read-only memory, right? There's some fixed table, and the lookups are literally just like reading cells of that entries of that table. It's like reads into a read-only memory. And so top level, like memory checking and lookup arguments they're literally the same thing. Okay, like very top level. The way Lasso actually works under the hood is the following. So this old literature on memory checking, they were trying to give efficient algorithms to force an untrusted prover to maintain a memory. And now they were focused on slightly different things than we care about in Snarkland. So they only cared about the space complexity of the prover. So they were thinking, look, we have a small of the verifiers. They were saying, like, look, we have like a verifier who has like almost no memory at all, so can't maintain a large memory on its own. So an untrusted prover is going to maintain the memory. The verifier is going to issue these requests to read and write to memory, and we need the verifier to be able to check that all of the answers the prover returns to these read requests are valid. And they came up with these nice fingerprinting procedures that let the verifier at all times kind of just maintain one fingerprint or something of everything it's seen so far. Now, in Snarkland, we don't care about a small space verifier, because the memory checking verifier in the old memory checking literature actually had to see all the reads and writes, but only forgot almost everything it saw as soon as it saw it. Right. In Snarkland, we'd be very, very unhappy. We wouldn't have succinctness if the actual Snark verifier had to see all the reads and writes. So you can't just directly say, oh, let's use the old memory checking algorithms, for a Snark, because the memory checking verifier needs to see all the reads and writes. It's just, a very small space. But it turns out that in Snarkland, the memory checking algorithms that made, the verifier small space are kind of exactly what you want anyway. So what we do in Lasso is we have the prover cryptographically commit to all the reads and writes, and for lookup arguments whatever. Lookup arguments are for read-only memories, but they inside the protocol there turn out to be writes anyway. Let's not get into those details. So the prover commits to all the reads and writes, so that the Snark verifier doesn't have to see all of them. That's the whole point of commitments, is to bind the prover to some large vectors, all the reads and writes, without actually explicitly materializing them to the verifier. And then we sort of conceptually just want a small arithmetic circuit that's able to sort of verify that the committed reads and writes are correct. Okay, and now this old procedure from the memory checking literature that ensured a small space verifier that did see all the reads and writes happens to just also directly turn into a small arithmetic circuit. So then you wind up just applying a Snark for circuit set, that takes as input all the reads and writes that the prover committed, and the Snark proves that those reads and writes passed the old memory checking procedure to check the validity of all the reads and writes. That is how Lasso works. Now, there's this extra wrinkle, which I think is really important and really simple to state now that, since this reading group covered the GKR protocol, which is the following cool thing. Once the prover commits to all the reads and writes, okay, there's no more non-determinism in this procedure, right? Committing to all the reads and writes, there's no extra advice inputs that the prover needs to, provide to this circuit implementing the memory checking procedure. So when I said, apply a Snark for circuit set, that's actually not accurate. You don't need a snark for circuit sat. Okay. Once the prover is committed to all the reads and writes, at that point, you only need like an interactive proof or argument for circuit evaluation. And in fact, it's sort of worse to use a snark for circuit sat because that'll have the prover like commit to more stuff. That it's not necessary for the prover to commit to any more stuff anymore because you're down to circuit evaluation. And so Lasso uses the GKR protocol, a very optimized variant like Thaler to what this particular circuit is doing, ultimately to, sort of make sure the prover correctly evaluated the circuit that implements, the old efficient, like memory checking algorithm from the, early 1990s. Were you able to follow that?
Yeah, makes sense. Not completely, but yeah.
Okay, cool. I think that's maybe roughly what I would have guessed. So I'll take that as a win.
Yeah, I guess I'll have to check the code to understand more. And there's also in the cost table, it's mentioned that Lasso is on the proof size is constant in the number of group elements, and like how big is the constant?
Oh, sorry. So it's so there's a sum check. Okay, so that's logarithmically many field elements right there. So I'm not. We shouldn't have said constant size proofs unless it was
It's logarithmic in the number of field elements and constant plus a constant group number of.
Well, we need a multilinear polynomial commitment scheme, and all of those are also log sized. So we still shouldn't have said constant number of group elements. So if we did, if you could actually point me to that, I'll definitely want to fix that. But the summary of what the proof size is there's the prover commits to a constant number of polynomials. Each commitment can be just like one group element, but there is ultimately one evaluation proof, and like all multilinear polynomial commitment schemes have log-sized evaluation proofs. So anyway, to summarize what the proof size is, so there's one sum check, so that's log many field elements. The prover commits to a constant number of polynomials, and there's certain ways you can kind of batch commit to them if you really care. So I don't know, you can either commit to each one individually, it's like one group element or something per polynomial, or you can sort of concatenate them all together into a single polynomial and then commit to that anyway. And then at the end of the day, there is one evaluation proof. By batching all of the polynomials together, you only need one evaluation proof. You don't need one for each. And how big is that evaluation proof depends on the polynomial commitment scheme used. So if you use something like zeromorph, which is sort of, multilinear analog of KZG, it'll be log size, log many group elements. The code base right now uses Hyrax. So for that, the commitments actually are square root size, and the evaluation proofs are square root size. But you can just swap it out for another polynomial commitment scheme with smaller proofs. So I can ramble on about my views on square root size proofs and why people shouldn't write them off. But anyway, hopefully at least my description of the verification costs are clear here. In general, I do think regardless of whether you have, Hyrax or Zeromorph or whatever, I think it's going to be quite reasonable to kind of wrap everything in the end in a gross 16 proof, if that's what people want to do to get the proofs to actually be a constant number of group elements. Does that make sense?
Yes. Yeah, I have no more questions for now. Thanks.
Yeah. And if you if there was anything in the paper that was unclear about the verification costs, I would appreciate a pointer, because definitely don't want to be unclear about it. Cool. Other questions? Okay. So based on my hard stop at 1, I probably should not try, actually then, sharing my screen and presenting anything. So hopefully just the verbal stuff was helpful and interesting. And it was valuable for me, for sure, since I have to prepare a bunch more material to try to make this stuff easier to kind of get up to speed on. So I guess I'll just say thanks a lot for coming, as always, and for the interesting questions. I definitely benefit from these discussions more than you all do. If you have any more questions, I'm happy to answer them asynchronously or talk about them at next meetings. I think I might have to just again cancel next week for the final cancellation, and then all of the summer travel is done and should get back to normal. I am having a kid, second kid, in a month or so we're going to have to navigate that as well. But at least there will definitely be no travel then, so it actually could be a good thing for consistency instead of a bad thing. Okay, so yeah, thanks a lot. I'll follow up in the chat on any follow-ups, and otherwise I'll see you in probably 2 weeks.
Congrats.
Yeah, thank you. Appreciate it.
Yeah.
Bye.
Congrats, and I'll see you 2 weeks in 2 weeks.
Yeah, sounds good. Talk to you soon.
Cheers, Justin. Yeah, congrats.
Thank you. Appreciate it. Bye.